Okay. All right. I think, okay, let me just give a quick introduction and then I'll hand it off to you. Hello, guys. I apologize for the delays. Um, but join me in welcoming Alexa Judaker-Martineau. She's a researcher at the Samsung SAT AI lab here in Montreal. Um, and welcome to the sampling reading group on the Blackboard, where we typically cover generative models and sampling methods, but we're also interested in broader topics because we always like to learn. So, but yeah, we're honored and excited to have you here presenting Less is More, recursive reasoning with tiny networks. Please give me a hand in welcoming Alexa.
Thank you for the presentation. Let me start this. No. All right. All right, so today I will present about the tiny recursive model, which made a big buzz online. If that's it's very clear. So okay, I will start with first the LLM money pit, then the new hope, which is the hierarchical model, and less is more, which is maybe I can actually use the mouse would be easier to the less is more approach, and some impact and future of this kind of direction. So the LLM money pit. Okay, so since the last few years, the message has been you should not pre-train, you should only fine-tune big models. There's no point. Everything has been invented. You should not. All the algorithm exists right now. It's just scaling. That's all it is. You should spend millions of dollars pre-training and fine-tuning on data. That's all you should do. That's the future. And the rich man experience is that LLM can solve math problem. They don't say it's high school problems though. That's if you don't know AIM, it's high school math problems. And so they show if you spend $4 million with RL, you can reach below the cutoff point for high school students with only 16 tries. So yeah, it's a fail, but this is claimed as a success. And my personal experience, which is not good, let's just say. So people always say, "Oh, let's try LLM for X, Y, Z," but it's super expensive. You need prompt engineering, and then simple baseline beats it. And then there's a project we did on molecule where we try to use chain of thought. So we say if the model can reason about making better and designing better molecule, maybe it will help. No, it doesn't. It cannot think about molecule and it's just super slow, super inefficient. And I also tried video games, so the JavaScript video game, so just code. So I found that small model like the small Quen, they all failed. They could not generate a game that was playable. There was always bugs all the time. And for it to work, you needed trillions of parameters, so the huge models. But then the problem is, okay, they work. But if you provide them extra assets, you say, oh, I have nice picture made by artists, for example, or audio or music or stuff like that. They're unable to integrate such asset because they just copy basically what they learn from the pre-training data. So if you have Grok has been trained on a lot of video games, so it can generate the video game it has seen in its pre-training. So, and it's the other, whoops, going too fast. The other issue is always fail at some point. Always. So that's why you see big trees with these LLM agentic system, because they have to kind of try many things in parallel. So many next step in parallel to find that, 90% fail. You just have to find the right one that doesn't fail, basically. So it's just filtering crap. That's the main job for agentic prompt engineering, basically. And so there's new hope, right? So the hierarchical model came out. It made a huge buzz because of the result, as you can see here. For example, on Sudoku or maze with small data, LLM cannot work, and direct prediction is pre-training a regular transformer from scratch doesn't work either. But and then the difficult ARC AGI puzzle logical benchmark, it also fails. While LLM can work very well for that, but it's just to say this approach is very small and yet could do very well on these problem. But the problem is with this approach, it's extremely hard to understand because everything is justified based on the brain, stuff like that. So this crazy figure that nobody understand is about comparing a mouse brain with this hierarchical model. So they find a way to compare and they say there's similarity to the mice brain. So this kind of argument makes it very, very difficult to understand how the approach works and why. I will try to simplify it, and I will show at the end that you can really, really, really simplify it. So you don't need the mouse brain. It's crazy. And okay, so but okay, let's go through it. So there's two parts. The first part is what we call the outer loop. It's the deep supervision. Okay, so if this n supervision is equal to 1, you can ignore z, then it's just function of x return y. So then and then softmax cross entropy. So nothing new, right? If n equal 1, this is regular training. But if n is higher than that, it's basically taking whoops, it's moving around too fast. Sorry about that. So it's taking initial z and return an x and then returning the output and the z, the result latent. And it detach it and take it back, carries it. The idea is to learn to emulate very large depth, so you can improve your answer over time. Instead of in one shot predicting the answer, you predict an answer, then you tweak it, you improve it, tweak it, and so on and so on. So this alone is the main benefit for their approach. It was shown in the ARC-AGI contest, where because it's not the author who did this, they show that it's 20% gain from doing that. And then, sorry. Okay, and then the inner loop now. So the inner loop is the much more complicated part, and it only accounts for 3% of the benefits. And it's effectively an architecture design. You can see that like this. It's a design where you have two networks instead of one. So you replace your regular transformer by two networks that are applied in different frequencies. So I don't know if you see, but you apply L, L, H, L, L, H. So like this, L, L, H, L, L, H. And for some reason, but I'll explain more later, sorry. It's only back propagating through the last two steps, the last L and the last H, these ones. I'll explain more why the argument that they give and why it's wrong. And basically, you see, this is small, this is big benefit. So there's some very interesting novelty from this approach, but I'll show that this part can be really improved because it's not clear. They say it's like the brains or something, but it's very unclear. And the benefits are very minor, but we can boost these benefits while making this much simpler. And the last thing about this, I know it's very complicated, okay? I don't expect you to all understand these parts. But okay, so if you do multiple supervision step, the problem is if you do 16 step, that means you spend 16 step on one data point, right? One example before moving to the next data example. So it's a bit wasteful, right? To spend all this time on one sample versus seeing much more 15 other samples, right? So the algorithm integrate all things complex Q-learning kind of approach where it says if I benefit, if I can stop, if stopping here is better than continuing, which is this Q0, Q1, then I just stop. And this is just used during training. This is just to say that basically instead of taking 16 steps all the time, then with this whole thing, you can learn to say, okay, I just need to spend maybe 4 steps on average and I'm good for most. It's just a way to reduce the time you spend per example, not to waste all this time. Okay, so that's HRM, but it's a bit more complicated than this. But this is the gist of it. And the main issue are, as I've mentioned, it's, I don't know if 111, but it's a complex argument. It's super complicated and there's no ablation. So it's hard to say why are things helpful. And there's twice the forward pass in this part. So in the outing, there's two, you see this HRM, it appears here and it appears at the top. So you have twice the forward pass. And the theorem about why they only backpropagate through the two last step, which was this part, right? These, why you only backprop through these two. It's all wrong, and I'll explain it. I'll explain. But I just want to say this HRM is really cool, right? It's really cool. It's just there's some issue with it. It's very it's not well explained, I think. Okay, so basically what they say is that okay, you apply L, then H, then L, and H. They say that if you do this kind of multiple iteration like this, you should reach a fixed point. So if you reach a fixed point, then at the last L network iteration, then if you assume that the latent basically doesn't change. I didn't mention that there's two latent just to simplify, but yeah, there are two latent, one produced by L and one produced by H. So your latent, that's why they call it hierarchical. Basically, if you assume this is a fixed point and the H also is a fixed point, then you can apply a theorem to say you can use one-step gradient approximation. So you can just not backprop with many loops, then it's a fixed point. You say if it's a fixed point, then I can just backprop to the last two steps like this. But it's not a fixed point. Okay, because they show this figure to say, oh, it's going to 0, right? It's getting, if you apply L, boom, 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 many times it gets to 0, right? And H, many times it gets to 0. But the problem is basically when you apply the theorem, you are here and here. So yeah, you did one H iteration, you did 2L and let's say 1H, 1L, and then that's it. You are here. You're nowhere close to any fixed point, and there's no reason why there would necessarily be a fixed point. There's no theory for well, you could assume that maybe it's not gonna cycle, but it could cycle, I don't know. In the end, it's clearly not a fixed point. There's massive residual. So it doesn't work. And like I said, 2 forward pass instead of 1. And the complex biological explanation for very little gain. And then we go to theorem, how to fix this issue and make it way more simple, okay? No need for any brain stuff. So, okay, the idea is instead of basically we define it this way, we define basically FL to recursively apply a few times. So it could be 2 like in the original paper or more. So it's just moving on your latent a few times, recursing. And then you have your final H that produce that H. So we define this whole thing as one full recursion process. And we backprop through this whole thing, not just the last 2, the whole thing. The point with this is that since you're using deep supervision, you learn to take any ZH, ZL to make a better answer Y. Whoops. So implicitly, you go through this whole thing and you make a better Y. That means any full recursion like this should improve your answer Y, which means you can then apply a few full recursion without gradient before doing your full recursion with gradient. So then you can still use this kind of idea of doing some step without gradients before doing one with gradient, but each step is a full recursion process because each of them is learned to improve your answer. So just a way to add a bit more, improve a bit your answer before back propagating through them. That's the idea. And this is the main boost for performance. This makes a huge difference. And okay, simpler interpretation, that's the one I like, because this whole thing is a mess. The ZH and ZL, because it's so complicated. H means high level, but high level is low frequency. It's very, and then the low level is high frequency, super confusing. So, but you can see basically ZH is just the answer. It's that simple. It's literally just the answer. So you're keeping track of your Y answer because ZH it's just applying an output L and using argmax to convert it back to the nearest token. It's just an embedding for your answer. That's all it is. It's the embedded answer. Meanwhile, ZL, well, it's the latent. That's the actual latent. That's the Z. So it's just Y and Z. And you can see it, for example, for Sudoku. If you have your input, which is your unfilled Sudoku, you have your filled Sudoku, which is your answer. And if you check ZH, it's just your predicted answer, right? It's just the answer predicted by your model. But ZL means nothing. It doesn't make sense. It's not decodable. It's a latent. So it's that simple. And then it simplified the whole thing because it's like you're always keeping track of your question, your current answer, and your current reasoning, latent reasoning. I call it reasoning. It's just a latent. And basically, you do the blue step, so you improve your Z. You go through a few paths of your network recursively. It's just, but with the weight sharing, basically. And then with your FL, and then you have your answer in your current latent, and you say, I'm just updating my answer based on the reasoning I did, basically. And then you go at it again. So that's all it is. It's just that's why you need X and Y, and it's just about it's better to always keep in mind your answer, to always remember where you're at right now and how you can fix any potential mistake. Unlike a LLM would once the token is generated, there's no going back. Okay, and basically, so it's Y and Z. Basically, it's that simple. But I wondered, what if we remove Y? So the problem is if we remove Y, then Z must memorize the answer. So you lose some capacity. It's better to have them separate. Always keep track of your solution. You don't want to be lost. And if you have multiple Z, which there's no reason for, but if the hierarchical paper, like they like this idea of hierarchy, and So if you wanted multiple Z, you could, because you do n forward pass through your FL network, so you could have one Z for each. But there's no need for that. I found like no benefit from either of those approach, and it's much simpler to just have Y and Z. Much more simple. And okay, the other thing that's cool is you can simplify more. You don't need as much layer, because I tried different width and depth, but I found that 2 layers was optimal, and even 1 layer can work actually, but you just need more expansion, more depth. So it decreased the parameter a bit too much, I think, but it can work. And by layer, I mean 1 layer, containing 1 MLP and 1 attention. It's not really 1 layer. It's like it's a bit more than that, but right, 1 transformer block basically, or 2 transformer block. And okay, and the other thing that's really cool. Okay, I thought, why do we need 2 network anyways? Because if you check, FL takes X plus Y plus Z to generate Z. And then this FH take Y plus Z to generate Y. So whether you have you give it X or not, it generates Z or it generates Y. Generate Y when it doesn't see X. So then it's kind of implicit from your input. So I figure you can just try the same network, it works as well. And I just want to be clear, some people ask me, why do you remove X? It's just a random choice, like you could keep X and add, let's say, an embedding that says, okay, this is an embedding to say this is the time that you should return your new solution or something like that. These all works, it's just, I think removing the X worked a bit better. It's not important detail, but the point is you need to tell the model somehow that this is the time to return the answer. So that's simplify it. You can even simplify it further. You remove the, because there was a continue loss with the Q-learning and stuff. No, you just have an outing loss, which it's just about predicting whether you are the correct solution or not. That's it. And then if you think, oh, I'm probably at the probability above 50% that I'm at the correct solution, then I stop. Very simple. This way you don't need to forward pass, because the other one was about what if I continue and stuff, but it's not needed. And you can add EMA for more stability. And for Sudoku, the MLP only architecture was much better, but it's specific to Sudoku, so it's not that important. And the algorithm looks like this. So you have the multiple outer loop with supervision, right? Which is about the same, but without the continue loss. And then the full, and then the deep recursion, it's just a few steps without gradient of the full process, and the final step with gradient. And the steps are like the n step on Z and the 1 step on Y. Refine your latent, refine your output. And okay, and the last thing about this algorithm is I wanted to find the optimal number of recursion, because again, there was no ablation in the original paper. So in the original paper, they did this. So two step for L, and two times they go through the whole thing. So 2L, 1H, 2L, 1H. So that's these 2 parameters. So basically, if you use 3 and 3, things get better. And with 2 layers, you can double the amount of time you spend per latent, because you have smaller network. So you can keep the same compute 2 times. So instead of 3, let's say 3 step for Z, you take 6 with 2 layers. It's the same amount of flops pretty much, and you get better performance. And you get the OOM, of course, if you go too large, because you backprop through the whole thing. But yeah, 3 is enough. 3 multiplied by 2. And the ablation look like this. So this is HRM. As you can see, you have 27 million parameter, but TRM gets much better performance with about double the depth because yeah, it's increased a little bit. And you see the main benefit is from the remote, not using this one-step gradient thing, instead going through the full recursion. That's the biggest thing. It was a mistake, I think. This fixed point idea was wrong. And otherwise, yes, more recursion and stuff. Yeah, for Sudoku, okay. For Sudoku, MLP was better, but it's very specific to Sudoku. So basically, the data set here is the toy ones. So we have 1,000 Sudoku, the very difficult one, with 1,000 data augmentation and a test set of a ton of Sudokus. And the maze is a bit crazier because I thought I was using data augmentation, but I learned 2 days ago that I was not using data augmentation. So it was set to false. So it's really just 1,000 maze, no data augmentation, nothing. And testing on 1,000 also hard maze. So it's quite impressive that it managed to reach 85% on the maze, considering only 1,000 maze. It's very surprising. It shows very good generalization. And so you see the 85, and that's for the attention network. So the MLP didn't work for maze, but for Sudoku, I mean. But for Sudoku, yeah, you see it's much better performance, whether you use attention or MLP with the TRM, and it's much smaller also. And then there's the ARC-AGI, which has a whole contest. If you don't know, there's a prize and this whole thing. And basically it's puzzle like this, where you have an input and output. So you see the goal here is to add the yellow and the missing of the square. So your goal is given the input, generate the output. And ARC1 is the easier one. ARC2 is this much harder version. But for a human, it's relatively easy. And the idea is you get each puzzle is like 2 or 3 X and Y examples. And you have one unsolved example like this one. And you could combine all of them together and say predict the missing one, but that's a bit high in context length. That would take a lot of power, I think. So to really make it easy, the cheap solution is just to learn a temporary embedding to represent each puzzle. This way you can solve the problem more easily. You just given the input, get the output. You have the embedding, so you know, okay, this is that problem, and yeah. And the results are here for ARC-AGI. So the TRM is here, the hierarchical is here. So with 4 times a smaller model, you get better performance. And similar for ARC-AGI 2, where we get much better performance. And all the other ones are LLM kind of thing. These two are Grok, but with complex setup, with evolutionary approach and stuff like that. But yeah, most approach are LLMs. And okay, this is okay, funny. So okay, so this is it for the approach. Now I quickly want to mention some funny stuff and the what it led to. So how this project came to be was project hashtag save the curve. So so my wife noticed that my curve was going down this year. So so she said it's unacceptable. So she gave me an extreme measure, which was I had 1 month to do 1 paper. very, very intense measure. And this is a quote from her. You lazy bum researcher shouldn't need 6 months to write one paper. Get to work and you can quote me on that. So yeah, so I had a lot of a very extreme measure. And it led to this paper. So clearly it worked. So that gave her argument that this was a good approach. Yeah. And I don't know if I will manage this month's paper though, and that will be hard. All right, and whoops. And the impact and future from this paper is just the takeaway that pre-training is not dead. You can still beat at specialized intelligence tasks like logic. You can still beat LLM by training from scratch. And that you can, whoops, sorry, you can go much smaller in a way that we reduce overfitting. It seems that going small and recursing really allows you to learn something about logic and intelligence, but without overfitting as much, without just memorizing the answer. Because like I said, 1000 maze, no data augmentation, and yet 85% of the test maze, it succeeds and it shows it's able to understand and generalize with very little data. And the benefit of going tiny is that you can research iteration go much faster. You don't need to rely on big corporation model, and it's much more efficient, much less costly. And TRN made a big news, made a big wave when it came out, because it sent the message that it wasn't not just about scaling, especially since things are fading a bit. People are starting to see LLM is not just the end-all solution, the final of everything. And the slides from my wife sent me. So, so basically, in October 2, in the Korean, because I work for Samsung, so in October 2, they closed down the market in Korea because of their national weeks. And so everyone was off. No, normally, if you check the previous year, nothing generally happens like much between the beginning or the end of the national week because everybody is not working. Nobody is working. But this time the paper came out and the Korean newspaper talked about it. I had emails from the VPs at Samsung saying, "Oh, we heard about it and we're excited." So and yeah, it basically gave a big boost in the stock market, which was even made more intense over time. And then also, yeah, I wanted to share this. This is from for some people on Twitter, Adam Ritter and Ben Hao Hung. I don't know if I said it properly. But basically, they show that you can scale this. It's very interesting because at training, the Sudoku, for example, is only trained on 16 improvement step to reach, in this case, 84% accuracy. But they show that since it learned to improve and improve and improve, it can keep improving, can keep fixing its mistake until it reached the cap is about 97, 98% accuracy. So you're learning to improve, to fix your mistake. And I think that's clearly an important part for intelligence that we don't see as much for LLM because of all the context that they generate cannot be regenerated. It's permanent. And the future direction could be to generalize it to other tasks. I've seen a paper on RL today, so it seems like it's possible to do RL. You could make it generative also, because right now it's deterministic. It's given an input, you get an output. So there's no generation here. It's purely deterministic. And there need to be some proof, right, Sebastian? We need some theorists to make some proof about why this space of recursion is so beneficial. And I mean, there's other things you can do. You could build an ensemble of tiny specialized model, for example, to get some kind of intelligence in a different way. Thank you. You have to try it.
Hello? Oh, it works. All right, great. Anyone have any questions? Oh, thank you, first of all. Anyone have any questions? I can run to you. So,
Hey, thank you for the great talk. It was very entertaining and informing at the same time. It's amazing. So do you mind if I ask you a little bit more questions in this course? Because, okay, so if I understand correctly, the training setting is that you only had those 1,000 samples.
Yeah.
And
Yeah.
so the generalization was only tested within the distribution, so to speak, within the domain that these 1,000 samples were generated in,
Yeah.
right? Okay, so I guess then the generalization of the model is like restricted in these domains, whereas like the LLMs like are more general. But nonetheless, being able to achieve that much like with 1,000 samples, like it's crazy. Right?
Yeah, and they are
Like-
very hard maze. They're set to take on average, take 100-ish step. They're set to be, so it's not an easy maze, right? It's not a maze where you're just gonna have a super short path.
So like the way that you serialize, that you tokenize this input, if it's tokenizing, right?
Right,
The
right.
transformer. How much domain knowledge does it have, for one question? The second is this entire intervention, like which is like completely deterministic, like resembles very much like old school deep learning when we did like architectural interventions, and I'm going back to ResNets and stuff like that. So this, like, how wrong would I be if I say that this looks like a ResNet where the block is kind of recursively applied to its own input?
Yeah, a lot of people say it looks a bit like RNN. A lot of people tell me that. So there's some kind of recursion, but it's just how it's set up. It's very, very specific. It's about having your answer and keeping track of it, and your latent. There's something that's different in
Right,
that way.
yes. And also if you can comment on the relationship with universal transformers.
Sorry,
Like,
Yeah.
that thing would be, you can comment on the relationship of PRM to universal transformer.
oh, I don't know. I haven't got through that yet. It's on my read list though.
all right. Just to could we keep it about 2 questions a person so we can get through everyone? Oh, limit.
Sounds
Second most. Yeah.
Thanks for the amazing talk. I might have missed it, but I didn't see an argument for why having less parameters was actually useful here. Were there scaling experiments
yeah,
done, or is it more of an OOM issue?
There's the ablation here. You can see with more layer, you get a bit less performance.
Oh,
It's actually better with less parameter.
okay, great.
So it seems to really benefit.
That's interesting. Thank you.
Thanks for the great talk. One thing which wasn't clear, like, is TRM also using one-step gradient, or is it an HRM?
No. There's no assumption about fixed, but you don't need fixed point theorem or anything like that. The idea was, let's go back. Okay, here is that you backprop through the whole thing. This is a full process that you backprop through, but you do a few of them of this full process without gradient, because you train this full process to improve your answer. So if it's always improve your answer in general, then you can use a few of them before you train, right?
So it's clear, it's in the beginning, there's for a few steps, there is no gradient.
Yeah, you
backdrop.
do.
After that, it is gradient.
Yeah, exactly. You do a few of them with a full process without gradient, and then one full process with gradient.
And in the ablation, do you have how important this is, like having those full?
Yeah, there's it's actually in the table. In this, the T represent the number. So if T is equal 3, it means you do. Whoops, it went too fast. If t is equal 3, it means 2 without gradient, 1 with gradient, basically. So they are in the ablation.
We're keeping the question over here. Amazing work, super inspiring. I saw the result of like the 16 limits to recurse being popped off, and it goes to
Right.
400. It seems there's still more juice to like get on this particular architecture.
Yeah, and let's go to it, the slide. So for training, I only use 16. I tried more, but it was never better. I don't know why. I think it spent too much time on one example. So it seems for training 8 or 16 is like optimal, but at test time you can crank it up. I think the people who have done this, they tried even more. I think they kind of stop at 98%. They could not kind of make it better.
So my question is, do you think that there's like some post training or like some inference scaling that you could do more to crank up the results still?
You could do, and for example, you can use the outing at inference also to know when to stop, but it's not accurate enough. So right now, generally, it's just better to do as much as you can, I guess. But yeah, there could be some post training. It's interesting idea.
I think, thanks for the talk. So if I understood correctly, what FH and FL have in common, like they get the Z and the Y as input.
Right.
But I have seen some really interesting approaches, more from like the computational neuroscience people, where they use hypernetworks. So FL or FH, for example, would sort of change the weights of the FL, which I think could be like really powerful. Have you thought of like trying that in this context?
It could be, since they are small, it could try hypertension.
Hi, so just to confirm, you train one TRM per task, right?
Per task.
As in, like, you're not training the same
Which,
multiple tasks.
yes, exactly. One for Sudoku, one for maze, one for.
Do you think
Yes.
TRMs could learn multiple tasks for the same weights, or do you see more future where you have separate TRMs for separate reasoning tasks?
Yeah, I wonder the same question. I don't know. It would be interesting to see in the future.
Okay, thank you.
Hi, thank you so much for the talk. I just had a question about the table where you had out of memory.
Yeah.
Can you explain that a bit more? Because from what I understand,
Yeah, the out of memory is because of the k, because n equal to k. So as you increase k to a 6, then you get out of memory, because it means 6 step. No, it's 6 multiplied by 2, so it's like 12 step for 12 layer, 12 step of 2 layers on improving z, and then 2 layers on getting your answer. It's just a lot of layer.
but I thought
So-
the improvement isn't back propagated through it. Like you only do back prop on like the
You
last
need to
control.
backprop through the whole thing. I did try backpropagating through only, like, let's say a k of the two. Let's say you have 12 step. I tried to backprop through only the 6 last step or something like that. It's in the ablation, the appendix, I mean, of the paper. I did try that, but that made things more complicated. Didn't work as well. It's much simpler to define a full process as a thing.
Thank you.
Hi, thank you for the talk. I have two questions. First, for the better performance of the smaller model, do you think that's explained by the fact that for Sudoku specifically, a smaller model is forced to learn the actual patterns while the larger model can sort of memorize the training data?
Yes, I think the memorization is a big thing. That's why recursing with smaller network is better. But we still need theory, right? But I think it's very clear. And the deep supervision also has a big effect on overfitting, because if you do only one step, it's like always input to output. then it's easy to memorize. But this prevents, in a way, memorization. But we need more theory for why and how.
Got it. And in the paper, I remember reading about a halting mechanism that you also had in the network.
Yes.
Could you tell us more about that?
Let me find it. Okay. It's here. It's basically, it's just adding final loss, which is when your prediction is equal to the true answer. It's that simple. When your prediction is correct, then you try to, that's your target, and you try with a small Q head, so a small head, to predict if that's true. Are you at the answer or not? And then sigmoid to it. So sigmoid to say if I have more than 50% chance that I'm at the right answer, I stop. It's that simple.
Got it. Thank you.
Nick online, you can ask your question if you want.
Hi. Yeah, fantastic work. I had a question in the TRM architecture. The X, the input, the Y, the previous predictions, and the reasoning are added together versus, say, concatenating together. I wondered why you chose to add them together versus concatenating.
Right. The idea is that if you concatenate, it's just your output is gonna vary also. It's not gonna, you're trying to only get Z or only Y. So you could concatenate, but you need to drop some output. Right now it works very well with this addition of the embedding. These are all embedded. So it's very, very simple. But yeah, there's other ways you could try.
Okay, it's interesting that they don't interfere with one another. I just it's some the fact that the input and the output are being added together sound. It's interesting. It's counterintuitive to me that that works. So it's yeah.
Keep in mind basically the input and I tried weight sharing, but you have to keep in mind right now they're not using weight sharing. That didn't work. So right now the input has a different embedding than the output, because the output depends on the reverse embedding here. So they're different. It's like in Quen how you have a different embedding for input and output. It's the same thing. So right now they are different. So this way the model can kind of separate the two and find some way of clearly knowing, okay, this is the input, okay, this is the output.
Okay, got it. Thank you.
Hi. Did you try just using pause tokens for Sudoku or ARC?
Pause token?
Yeah. It's a trick where you just have the model pause and then recurse.
I did not try that. I know I think I used some paddings and the attention that was not useful, I think. To create attention sync or something.
No, it's more to implement like a recursive operation where it just doesn't generate the output. It just takes a pause and then it runs through the whole cycle of the transformer again. And then it potentially says a pause again. You can inject as many as you want and you can achieve some similar kinds of recursive operations.
But wouldn't you need to backprop multiple times to that?
Yeah, but you could train it with pause tokens in the mix.
Okay. Yeah, I haven't tried that.
Yeah. Might be interesting to check it out.
Look, would you mind if you want to? Would you like more questions or like? Are you like? I don't know. You're good with more questions. Okay. Is there any more questions online? I guess before. 1, 2. Okay, cool. I think okay, we have one question over there, and I just have one question, and I think we'll just stop it there.
Thank you so much for the presentation. It was excellent. So HRM has their rationalization for why their approach works through brain, etc. Do you have your own line of thinking or hypothesis about why your particular approach works so well for being so small compared to these enormous models that it's competing with? I know you had mentioned improved generalization and overfitting in the recursive PERDA.
Yeah, one part I would say is this deep recursion and this recursion with many recursion with small network to prevent overfitting. That's one big thing. And the other is just more intuitive, right? It's better to keep track of your answer, not just have some latent, some input to output. You always have some answer, and then you can rethink: is this answer logical, or is there some error? It makes a lot of sense to reason this way, rather than some black box way. It's better keep track of where you are, rethink and rethink and tweak it basically.
Right, thank you.
Okay, I have a question. I see a lot of similarities to like modern day generative modeling, like flow matching and diffusion, where they have like this, you have some vector field that kind of recursively like refines the input, right? But in this case, you have an augmented state where you also you update the latent. I was wondering if you had any thoughts about this.
So about diffusion, the thing with diffusion is you're just trying to generate the data. So diffusion is kind of cool because in the training you don't need to backprop too many steps, but it's such a way so that at inference you can use many steps, but you don't need to backprop through them all. There's a trick to do that, so it's one shot. But the thing though is that it's still just learning to generate denoise the data. So ultimately it's not really thinking in a logical way. In this way, it's really about tweaking your answer, improving your answer. Because if you have you use diffusion to generate images, if you just noise some parts and denoise them, it could be better, it could be worse, right? It's not necessarily gonna be better. But this one is really about backpropagating through improvement. So that's the
Okay, thank you. All right. Please join me one more time in thanking Alexa. Thank you so much for the presentation, and sorry about the trouble in the beginning.